Derivations of equation of motion of a vibrating system can be done using two methods. The first one is the Allenberg principle, which states that the resultance of the inertial moment of the system is equals to the resultance of external moment applied to the system. And the second one is what it is presented in this video called system equivalent analysis, where this is based on the total energy of the system. It is the kinetic energy, which relates to the mass and inertia of the system, the potential energy, which relates to the stiffness of the system, and the work done, relating to the damping of the system. So let's see again, if we have a system with mass m and second mass moment of inertia j, the stiffness of the system is represented by springs with stiffness constant k and damper with damping constant c. The system is rotating around the center of rotations, and the linear displacement of the center of gravity is x. And if we choose x as the generalized coordinate, then the kinetic energy can be defined as T equals to half equivalent mass x dot square. The potential energy is defined as U equals to half equivalent stiffness x square, and work done is defined as W equals to minus integral equivalent damping constant x dot dx. After obtaining all the equivalent parameters, from here, the equation of motion with generalized coordinate x is equivalent mass x double dot plus equivalent damping constant x dot plus equivalent stiffness constant x equals to 0. Very straightforward. Similarly, for the same system, if we now take the angular displacement theta as the generalized coordinate, the kinetic energy now defined as T equals to half equivalent second mass moment of inertia theta dot square, the potential energy as U equals to half equivalent rotational stiffness constant theta square, and the work done as W equals to minus integral equivalent rotational damping constant theta dot d theta. Thus, the equation of motion with generalized coordinate theta can be written as J equivalent theta double dot plus C equivalent theta dot plus K equivalent theta equals to 0. Simple, isn't it? The good thing about this method is that we don't have to worry about the directions of force. But the method is best for the single degree of freedom system and becomes more complicated for higher degree of freedom system. See you in the next video.